Welcome to the class. Today we will talk about the examples related to steam power cycle, which is actually Rankine cycle for us. So the first example says that a steam power cycle operates on Rankine cycle between boiler conditions of 4 megapascal and 300 degrees Celsius and the condenser pressure of 50 kilopascal. Find cycle efficiency, work ratio and steam rate. We will first draw the Rankine cycle for our reference, and then we would note all the numbers. This is 1, this is 2, this is 3 and this is 4. So this is the Rankine cycle for us. So as per the given conditions, P2 is equal to P3 is equal to 4 megapascal. So it is given. Then T3 is equal to 300 degrees Celsius and P1 is equal to P4 is equal to 50 kilopascal. We are supposed to find out cycle efficiency and work ratio and steam rate. So in view of this, we can proceed with the example, and here we need to first go to the steam table and then find out what are the properties at different stations. What properties we can find out from the steam table? We can find out definitely the property 3, okay, and property 3 would correspond to, if I go to the steam table for the 50 kilopascal. So steam table we had discussed that there would be different sections, and initially we would have a section where based upon the saturation temperature we can find out the enthalpy, entropy, internal energy, specific volume. In other section we had seen that we can find out the same parameters based on the saturation pressure. But after these two sections there will be superheated section where we would be given with saturation pressure and different superheat temperatures. For each case there will be same parameters as entropy, internal energy, specific volume would be mentioned. So one state corresponds to the saturation liquid. So we can go to 50 kilopascal condition in the same table and find out what is the enthalpy at state 1. So if we say H1, which corresponds to enthalpy at 50 kilopascal saturation liquid, is equal to 340.49 kilojoule per kg. Then we will also mention specific volume at state 1, which again corresponds to specific volume corresponding to 50 kilopascal saturation liquid, and this specific volume turns out to be 001030 meter cube per kg. We would also need entropy since process 1 to 2 is isentropic, but we don't need entropy since we can find out state 2 using the assumption of flow to be incompressible, and then we can find out the work input. So for that we can find out WP, which is pump work, and we know we are going to use formula V1 into P2 minus P1. So using this formula we can mention 0.001030 into meter cube into 4000 kilopascal, which is 4 megapascal minus 50 kilopascal. So this is into 10 to the power 3. So we can get pump work to be around 4.0685 kilojoule per kg. So we can find out H2 is equal to H1 plus pump work. H1 is known to us, 340.49, pump work is 4.0685, so we get H2 344.56 kilojoule per kg. Now we need to find out state 3. So for finding out state 3, we need to go to the steam table. In the initially the part which deals with the saturation pressure 4 megapascal, we have to see what is the saturation temperature, and we have to compare that saturation temperature with our given saturation temperature. If our given saturation temperature is basically more, if our given temperature is more than the saturation temperature, then we have to go to the superheated part. So we will obviously go to the superheated part in the present case, and then we will find out what is H3 from the steam table, and H3 from the steam table is 2960.5 kilojoule per kg. But here we would also mention S3, which is entropy at 3, and this is 6.3615 kilojoule per kg Kelvin. This is our entropy at station 3. Now we can find out the state 4, but for finding out state 4, we just first have to compare the fact that S4 is equal to S3. Now how should we proceed here? We will go to the steam table, we will go to the first the pressure part of the steam table, where we are told that the condenser pressure is 50 kilopascal. So we will find out what is the saturation fluid entropy or saturation vapor entropy for the 50 kilopascal case. And now if our S3 is greater than that, then we would understand that the point 3 is in the superheated part. But if our S3 is less than Sg, then we are in the wet dome as it is shown over here. So we might sometimes, if 3 is somewhere here, then we might end our 4 point over here. So in this case we will have to go to the superheated part corresponding to 50 kilopascal, find out at what temperature in the superheated part corresponding to 50 kilopascal the entropy matches with the entropy S3, and when it matches, that state, that temperature at 50 kilopascal is the state 4 condition. But here it would turn out that S4 is basically equal to S3 and S3 is less than Sg at 50 kilopascal. So we have to find out the dryness fraction at state 4. So S4 is equal to Sf plus X into Sfg is equal to S3, and S3 is 6.3615, and then we can know what is Sf and what is Sfg, which is the latent entropy required for phase transfer. So knowing Sf, knowing Sfg from the steam table, we can find out X. So here we get X is equal to 0.81. So this is dryness fraction at state 4. So knowing this dryness fraction, we can find out H4 as H1 plus X4, which is basically this X4 into HFG, and then we know H1 is 340.49 plus 0.81 into HFG if HFG is given, otherwise we can make it as HG minus HF, which is basically saying that HFG is equal to HG minus HF. This is saturation enthalpy vapor, this is saturation enthalpy liquid. So knowing this, we can find out H4 is equal to 340.49 plus 0.81 into Hg is 2645.9 minus 340.49, and this gives us H4 as 2207.87 kilojoule per kg. Now we know enthalpy at 1, enthalpy at 2, enthalpy at 3 and enthalpy at 4. We also had found out what is pump work. So now we can proceed and find out other work and heat interactions. So we can find out what is basically initially Q in, which is heat added, which is H3 minus H2. So H3 is equal to 2960.5 minus H2 is equal to 344.56, and this gives us H delta H or Q in as 2615.94 kilojoule per kg. We can also find out Q out, and Q out will be H4 minus H1. So H4 is known to us 2207.87 minus H1 is 340.49, and this gives us Q out as 1867.38 kilojoule per kg. So we can find out thermal efficiency of cycle as 1 minus Q out upon Q in. So it is 1 minus 1867.38 divided by 2615.94, and this gives us efficiency as 28.6%. So we can find out also turbine work, and turbine work is H3 minus H4. H3 is 2960.5 minus H4 as 2207.87, and this gives us turbine work as 752.63 kilojoule per kg. Pump work is already found out, so we can get W net, and W net is Wt minus Wp. So 752.63 is turbine work minus pump work as 4.0685. So we get net work as 748.56 kilojoule per kg. Knowing this, we can find out the asked thing, which is work ratio and steam rate. So we can find out steam rate. Steam rate is equal to 1 upon W net, which is specific work. So it is 1 upon 748.56. So it is 0.001336 kg per kilowatt. So then we can find out work ratio, and that is W net upon WT. So W net is 748.56 and WT, which is turbine work, 752.63. So we get it as 0.995. So this is how we can solve the example. Here we have to also remember one more point, that suppose in the present case we need to find out the condition at 3 from the steam table, and then in the steam table if 300 degrees Celsius superheat temperature is not available corresponding to 4 megapascal, and if we have 350 and 250 temperatures given, then we can interpolate and find out the condition at our required desired condition of 300 degrees Celsius. So we need to practice for the fact that if some data is unavailable from the given data, we should extrapolate or interpolate to get the conditions required. We will move ahead to the next example, which states that a steam power cycle operates between boiler conditions of 3 megapascal and 350 degrees Celsius and condenser condition of 75 kilopascal. Find heat and work interactions and also cycle efficiency. So example for practice is almost similar. We are given that we are having now boiler condition as 3 megapascal. So state 2 and 3 pressures are given. So P2 is equal to P3 is equal to 3 megapascal and T3 is equal to 350 degree Celsius. We are told that P1 is equal to P4 is equal to 75 kilopascal. Again, as what we did for the first example, we have to go to the steam table and then find out enthalpy corresponding to 75 kilopascal saturation liquid, and this would have value as 384.44 kilojoule per kg. Here we also need to find out specific volume at 75 kilopascal saturation liquid specific volume, and this will be 0.001037 meter cube per kg. Then we can do one thing, we can find out first pump work, and pump work is nu 1 into P2 minus P1. So it is 0.001037 into P2 is 3000 kilopascal minus 75 kilopascal, so it will 10 to the power 3 pascal. So we will have pump work as 3.03 kilojoule per kg. Hence we can find out H2. H2 is equal to H1 plus pump work. So H1 is 384.44 plus 3.03, and this gives us H2 as 387.47 kilojoule per kg. So we know now state 1 and state 2. So now we need to find out state 3. So we will go to H3, and obviously as expected we will compare we will first see what is the saturation temperature corresponding to 3 megapascal, and it would turn out that our given temperature 350 degrees Celsius is more than that. That is why H3 we are seeing in steam table in the 3 megapascal and 350 degrees Celsius superheat for enthalpy, and this gives us value of enthalpy as 3116.1 kilojoule per kg. There itself we will see entropy at state 3, and entropy at state 3 will again be at 3 megapascal, 350 degrees Celsius superheat, and then this we will have entropy as 6.7450 kilojoule per kg Kelvin. Now again we have to know that we have S4 is equal to S3, which we will see that if this S3 is greater than Sg at 75 kilopascal, or S3 is less than Sg at 75 kilopascal, and accordingly we will see which part of the steam table should be seen. So in our case S3 remains less, so we will see such the steam table in the saturation part, and then we are not in superheated part. So then we need to find out the dryness fraction. So it turns out that S3 is known, which is 6.7450 is equal to S1 plus X4 into SFG, and SFG at 75 kilopascal. So we will see in the steam table what is the liquid saturation enthalpy at what is the liquid saturation entropy S1, what is the latent entropy SFG corresponding to 75 kilopascal, and from that we will get X4, and X4 turns out to be 0.8861. Knowing this, we can find out H4, which is H1 plus X4 into HFG at 75 kilopascal. So this gives us, suppose HFG is given, so we first know H1, which is 384.44 plus X4 is 0.8861, and HFG, it would be known to us from the steam table, it is 2278. So this gives us H4 as 2403.0 kilojoule per kg. Now we know all enthalpies at all corners of the cycle. Now we can find out what is Q in, what is Q out. So Q in is equal to H3 minus H2, and H3 is 3116.1, H2 is 387.47, and this gives us Q in as 2728.6 kilojoule per kg. Similarly, Q out is H4 minus H1, and we have H4 2403 minus H1, which is 384.44. So Q out is 2018.6 kilojoule per kg, and this gives us all the numbers required to find out thermal efficiency of cycle, which is 1 minus Q out upon Q in, So which is 1 minus 2018.6 divided by 2728.6, and thermal efficiency would be 26%. So this is the value of thermal efficiency for the given example. Then we can find out Wt, which is turbine work, as H3 minus H4, and H3 is 3116.1 minus turbine work minus H4, which is 2403, and this gives us turbine work as 713.1 kilojoule per kg. So we have net work as turbine work minus pump work. This is turbine work, and then we found this as pump work. So we have 713.1 minus 3.03, and this gives us net work as 710.1 kilojoule per kg. This W net we would also have got if we do Q in minus Q out is equal to basically W net, which is Wt minus Wp. Similarly, we would also have got efficiency by saying W net upon Q in. So these are the different ways by which we can find out different parameters which are asked in the question. We will go ahead with the next example, and it states that a steam power plant which operates between the boiler condition of 3 megapascal and 400 degrees Celsius and condenser condition of 10 kilopascal. Find thermal efficiency and power output. Find same parameters if superheat is 400 degrees Celsius. Find same if the superheat, if the boiler pressure is raised to 10 megapascal and turbine inlet temperature is 400 degree Celsius. So basically there are 3 examples in the same example. So let us see what to do for the first part. So for the first part, we will first draw TS diagram. So this is for the first part. In second, we would have told that the temperature is risen. So we have to find out new condition. In the second part, rather in the third part, we are told that boiler pressure and boiler temperature both are increased. So these will be 3 conditions. This is 1, this is 2, and this is 3. So having said this, these are the general numbers. So in the given case, for present case, we have P2 is equal to P3 is equal to 3 megapascal T3, and we also have P1 is equal to P4 is equal to 10 kilopascal. In example A, T3 is equal to 400 degrees Celsius. In B, T3 is equal to 500 degrees Celsius, and in C we have T3 is equal to again 400 degrees Celsius, but P3 is equal to P2 is having raised value of 10 megapascal. So we will solve first A. For A, we have to first find out H1, and H1 turns out to be 191.83 kilojoule per kg. Similarly, V1 is equal to 0.001010 meter cube per kg. So we have Wp is equal to nu into P2 minus P1. So it is 001010 into P2 is 3000 kilopascal minus 10 kilopascal. So pump work will be 3.0199 kilojoule per kg. So H2 is equal to H1 plus Wp. So we have 191.83 plus 3.0199, and this gives us 194.85 kilojoule per kg. This is our H2. So we have to go into the steam table and note down what is H3, and in case of 3 megapascal, so at 3 megapascal and 400 degrees Celsius superheat condition, we have H, which is H3 as 3230.9 kilojoule per kg. Similarly, S3 at 3 megapascal and 400 degrees Celsius superheat, S3 is equal to 6.9212 kilojoule per kg Kelvin. म्हणून we, so we have S4 is equal to S3, and then again knowing the fact we will write it as X4 into SFG plus S1 at 10 kilopascal. So we will get these two things at 10 kilopascal. We can find out from the steam table, where this is liquid saturation entropy, this is the latent entropy, and then we know it is equal to S3, which is 6.9212, and this gives us X4 as 0.836. So we have H4 is equal to H1 plus X4 into HFG. This helps us to find out what is the enthalpy, and so enthalpy is 2192.27 kilojoule per kg. So we now have everything, H4, H3, H2, H1. So all corners are known for the example number 1. So we have Q in is equal to H3 minus H2, and then that Q in is 3230.9 and 194.85. So this is 3036.05 kilojoule per kg. Q out is equal to H4 minus H1. So H4 is 2192.27 minus H1, which is 191.83. So we will get Q out as 2000 0.44 kilojoule per kg. So thermal efficiency is equal to 1 minus Q out upon Q in. So 1 minus 2000.44 divided by 3036.05. So we get 34.11% efficiency for the first case. We can go ahead and do the calculation for the rest of the cases in the similar way. So we will go ahead, and for part B we can write down the enthalpy H3. It should be remembered over here that for part B we are not changing the boiler conditions. So if we are not changing the boiler inlet conditions, then H1 is same, and H1 is 191.83, H2 is same 194.85, but H3 is not same. We have to go back into the steam table, see in the superheated part corresponding to 3 megapascal, and lastly we had seen for 400, but now we have to see for 500 degrees Celsius, and we have to mention H3 as 3456.5 kilojoule per kg. Similarly here we will mention S3 also, and S3 will be 7.2338 kilojoule per kg Kelvin. Knowing this, we can also again say S4 is equal to S3 is equal to S1 plus X4 into SFG, which is equal to 7.2338, and this gives us X4 as 0.878. So we can find out H4, and H4 is H1 plus X4 into HFG. So we know that it is 191.83 plus 0.878 into HFG. In case if it is not given, we can make it as HG minus HF. So it is 2584.7 minus 191.83, and this gives us H4 is equal to 2292.77 kilojoule per kg. So we can find out Q in, which is H3 minus H2. H3 is 3456.5 minus H2 is 194.85. This gives us Q in as 3261.65 kilojoule per kg. So we have Q out is equal to H4 minus H1, so 2292 minus 7.77 minus 191.83, and this gives us Q out as 2100.94 kilojoule per kg. So efficiency is equal to 1 minus Q out upon Q in, and we know 1 minus 2000.94 divided by Q in 3261.65, and this gives us efficiency as 35.59%. So we can compare two efficiencies, and in the first case we had efficiency 34.11%, and for 34.11% turbine inlet temperature was 400 degrees Celsius. But now we solve the same example for turbine inlet condition of 500 degrees Celsius. So it should be remembered here that if we increase the turbine inlet condition for the same condenser condition, then we will have more mean temperature of heat addition, and that would lead to increase in efficiency of the cycle. So we have third part remained in the same example. So here we know that is C part, we have H1 will be same, that is 191.83. But now we have to work out for with the boiler of 10 megapascal pressure. So H2 we have to find out for 10 megapascal condition, where we know we had also written down V1 and it is 001010. So we can find out pump work is equal to V1 into P2 minus P1. So it is 001010 into, we have now 10 megapascal, so 10,000 kPa, and we have only 10 kPa for the condenser pressure, so it is 10 to the power 3. So we have pump work as 2. So pump work turns out to be 10.08999. So we have H2 is equal to H1 plus pump work and H2 over here, that's why it will be 201.92 kilojoule per kg. So we know now two corners. We have to find out H3 from the steam table, and H3 is enthalpy at 10 megapascal, and in the example temperature is given as 400 degrees Celsius. So and 400 degree Celsius superheat, and that enthalpy H3 would be 3096.5 kilojoule per kg, and here we remember that we have to also find out entropy corresponding to 10 megapascal 400 degrees Celsius superheat, and then this entropy is 6.2120 kilojoule per kg Kelvin. So we have S3 is equal to S4 is equal to 6.2120, which is S1 plus X4 into SFG. So this gives us idea for the value of X4, and then this is 0.742. So we should remember here that as we have plotted over here, so we kept the same turbine inlet temperature as 400 degrees Celsius, but we increased the boiler pressure from 3 megapascal to 10 megapascal, from 3 megapascal to 10 megapascal. We can see that we got decrement in the dryness fraction. In the first case we had dryness fraction where we found out X4, and X4 was 0.836, and in the last example for the same boiler pressure, when we increased the turbine inlet temperature, we should see that the dryness fraction increased. So later we got X4 as 0.878. So we can make a small conclusion over here. In the first, if we compare example A and B, then X4 we got increased since we have T3 increased. And now if we compare here and make a small conclusion that if we compare example A and C, then X4 decreased for the case that we increased P2, which is also equal to P3, and this is increased for same T3, and here also it is for same P2 is equal to P3. For same P2 or P3 we got this conclusion. So now we can move ahead and find out H4, which is H1 plus X4 into HFG, and this gives us value as 1967.34 kilojoule per kg. So we can then now know everything H1, H2, H3 and H4. So Q in turns out to be H3 minus H2. So it is 3096.5 minus H2 201.92, and Q in is 2894.58 kilojoule per kg, and Q out is equal to H4 minus H1, where H4 is 1967.34 and H1 is 191.83, so it is 1775.51 kilojoule per kg. So we have thermal efficiency as 1 minus Q out upon Q in, which is 1 minus 1775.51 divided by 2894.58, and this gives us efficiency as 38.66. So this is our efficiency. Here as well we can make a small conclusion when we compare example A and C. We can see that thermal efficiency has got increased from value of 34.11 to 38.66 for same T3 and increase in P3, since here as well mean temperature of heat addition has got increased. We will move to the next example. This example states that a steam power cycle operates between boiler condition of 3 megapascal and 400 degrees Celsius and condenser pressure of 10 kilopascal. Find cycle efficiency and mass flow rate if the turbine efficiency is 85%, pump efficiency is 80% and power output is 20 megawatt. So again we will do from the scratch, where we will first draw the TS diagram for the cycle, where we will denote all the points 1, 2, 3 and 4. So given things for us are P3 is equal to P2 is equal to 3 megapascal, T3 is equal to 400 degrees Celsius, and we have P1 is equal to P4 is equal to 10 kPa. But now we are told that the pumps and turbines are not ideal. So what we should do is, for ideal case we will mention them as dash, and then really 2 will be here and then 4 will be here. This is 4 dash. So practically P2 is equal to P2 dash is equal to 3 megapascal and P4 is equal to P4 dash is equal to 10 kPa. Turbine efficiency is 0.85, pump efficiency is 0.8. Now we will proceed. We can find out H1 which is H corresponding to 10 kPa and saturation liquid. So this H for us we can find out, we can get it from steam table, and then this H we can further use for the calculation of H2, which is the enthalpy at the outlet of the turbine, of the compressor. In this example we will start with finding out the pump work. So pump work, which is ideal, we know it is V1 into P2 dash minus P1, but P2 dash is same as P2, so we can use either. So we can see V, and this V is specific volume corresponding to saturation liquid at 10 kPa, and this turns out to be 0.001010. So P2 dash is 3 megapascal, so 300 kPa minus 10 kPa into 10 to the power 3 in terms of Pascal, and then this will give us turbine pump output in ideal sense, but now we want pump output in real sense. So for that we can make use of the fact that WP dash, which is pump output, WP, which is real pump output, is equal to WP dash divided by 0.8 or WP dash divided by pump efficiency. So we can say that WP is equal to WP dash upon pump efficiency. So 0.001010 into 3000 minus 10 into 10 to the power 3 divided by 0.8. So this gives us pump work, which is real pump work, and real pump work turns out to be 3.77 kilojoule per kg. Now we can find out turbine work. Similarly, real turbine work is equal to ideal turbine work into turbine efficiency. So ideal turbine work, we know that it is equal to H3 minus H3. Ideal turbine work is H3 minus H4 dash into turbine efficiency. So now we can find out H3 from the steam table. We can go to the conditions 3 megapascal. We will go into the superheated part and see the temperature 400 degrees Celsius, and we can get H3. So this H3 can be found out from steam table. This turns out to be 3230.9, and this is superheated part corresponding to 3 megapascal and 400 degrees Celsius. Now we need to find out H4 dash, but H4 dash is inside the dome, so we don't know what is the wetness or what is the dryness fraction. For that, S3 is equal to S4 dash. So we need to find out S3 also from the steam table corresponding to 3 megapascal and 400 degrees Celsius in the superheated part of the steam table, and then we can write it as S1 plus X4 into SFG, where S1 is the entropy of liquid saturation corresponding to 10 kilopascal, SFG is latent entropy corresponding to the 10 kilopascal pressure. So knowing this and knowing left hand side, we can find out X4, and X4 turns out to be around 0.83. Now knowing this, we can find out H4 dash, which is equal to H1 plus X4 into HFG, where H1 is the enthalpy corresponding to liquid saturation at 10 kilopascal, and H Fg is again latent enthalpy at 10 kilopascal. So having said this, we can find out H4 dash from all these numbers known, and it turns out to be 2192.21 kilojoule per kg. Having said this, we can find out now turbine work as it was expected. So turbine work is equal to Wt dash into turbine efficiency. So Wt dash is H3 minus H4 dash into turbine efficiency. So H3 is known to us 3230.9 minus 2192.21 into 0.85. So we will get turbine work as 882.89 kilojoule per kg. So this is the turbine work. Now we can find out W net, which is the net work, and that net work is turbine work minus pump work. So it is 882.89 minus 3.77. So we know net work in this case is 3879.12 kilojoule per kg. Now we know this network, we can find out the mass flow rate and also efficiency. So for mass flow rate, we know W net, which is m dot into small w net, and this is told to us as 20 megawatt. So 20 into 10 to the power 3, it is kilowatt. So we can say W net is equal to m dot into small w net. We have found out it as 879.12 is equal to 20 into 10 to the power 3. This is right hand side is in kilowatt and left hand side this unit is kilojoule per kg, and m dot is in kg per second. So we get m dot as 22.75 kg per second. Now for efficiency we need Q in, and Q in we know is equal to H3 minus H2. So H3 we have known to it as 3230.9. H2 is H1 plus pump work. So H1 can be found out corresponding to the liquid saturation enthalpy at 10 kilopascal condenser condition. We have found out the pump work. We need to add that and then get H2. So H2 turns out to be 195.59. So Q in for us is 3035.31 kilojoule per kg. So efficiency of the cycle is W net upon Q in. So it is 879.12 divided by 3035.31. So efficiency turns out to be 28.96%. So we can find out the cycle parameters if at all we don't have ideal components of the cycle. We will move to the next example, and this example reads that there is a steam power cycle in which boiler conditions or turbine inlet conditions are given as 15 megapascal, 600 degrees Celsius and condenser pressure as 10 kPa. Find out heat and work interactions and also cycle efficiency if turbine efficiency is 87% and pump efficiency is 85%. Evaluate net power output if mass flow rate is 15 kg per second. This example is reverse. In earlier example, mass flow rate was to be found out and total power output was given. Here we have to find out total power output, and we are given with mass flow rate. So we will start. As in earlier case, we will make this as 3, this as 4 dash, 4, 1, 2 dash and 2. So this is our cycle. Having said this, given things are P2 is equal to P2 dash is equal to P3 is equal to 15 megapascal. T3 is equal to 600 degrees Celsius. P4 dash P4 equal to P1 is equal to 10 kPa. Turbine efficiency is 87% and pump efficiency is 85%. M dot is 15 kg per second. Now, as expected, we should go and find out H1, which is enthalpy corresponding to condenser pressure, and it is liquid saturation enthalpy, which is 191.81 kilojoule per kg. Similarly, specific volume at the same condition is 0010 meter cube per kg. So we can find out WP, and then that is WP dash divided by pump work. So that is nu 1 into P2 minus P1 or P2 dash minus P1 divided by pump efficiency. So we get pump efficiency from here 0010 into 15 into 10 to the power 3 kilopascal minus 10 divided by 0.85, and we get pump work as 17.63 kilojoule per kg. So we can get H2 from here as H1 plus pump work, and it is 209.44, that is kilojoule per kg. Having said this, we can find out H3, which is the superheated enthalpy at 15 megapascal and 600 degrees Celsius, and this is 3583.1. We will immediately note entropy at the same state, and that entropy will be 6.6796 kilojoule per kg Kelvin. So we know that S3 is equal to S4 dash, which is equal to S1 plus X4 into SFG. So we have S4 dash, which is 6.6796 is equal to S1, again from steam table 6492, corresponding to liquid saturation entropy at 10 kilopascal, into SFG is 7.4496. So we get X4 is equal to 0.8094. Knowing this, we can find out H4 dash, and H4 dash is equal to H1 plus X4 dash into HFG. So we get it as 191.81 plus 0.8094 into 2392.1. So H4 dash is equal to 2127.97. Having said this, we can find out basically here the turbine work in real is equal to turbine work ideal into turbine efficiency. So it is H3 minus H4 dash into turbine efficiency. So H3 is known to us. We have noted it as 3583.1 minus 2127.97 into 0.87. So we get real turbine work using this as 1265.95. Then we can go ahead and find out Q in, which is H3 minus H2, and H3 is basically 3538.1 minus H2, and H2 we have noted down here as 209.44. So Q in for us is 3373.66 kilojoule per kg. So we can find out cycle efficiency, which is W net upon Q in. So W net is WT minus WP divided by Q in, and this gives us W net first as 1265.95, which is turbine work, minus pump work, which is 17.63 divided by 3373.66. So W net is 1248.3 divided by 3373.66, and this gives us cycle efficiency as 0.37 or 37%, and then total W net is equal to m dot into specific W net, and m dot is given to us as 15 into W net is here 1248.3, and then this is 18.72 megawatt. And this is how we can solve the example if we are having the cycle which has simple components or maybe the components which are non-ideal, and these cycle examples are actually not dealing with any attachment. Thank you.